I believe it's me. Yes, draft physics. Yeah, that's it. Video production. Comments and such, and then some photon stuff. I believe going to be photons for a while. Um, yeah, just sort of go to the basics. Back to the beginning. And what do we know about these things? And we know a lot. Yeah, but just not quite enough yet. All right, anyway. So this is Sir, Please Calm Down, which is hilarious. One of these wearing a cap fellows with a beard. It's already kind of suspicious. Well, let's see. Hallucinogens have fully ingrained themselves in your head, haven't they? My 2 cents for what it's worth. And what do you think it's actually worth? Frankly, what? Some anonymous whatever douchebag shows up and insults me. Oh, thank you. And like, what do you? I mean, I could just do this, on your videos. What are you wearing a cap for? Is your brain so rotten that it stinks that bad? You trying to cover up the stink? I mean, what's the point? So this is Bicycle Boy. I'll just call you something else, right? It's got I quit my job at the bike shop, where we just did wheelies all day. I quit my job, because obviously, we're not selling any bicycles. And he's a breeder, right? On a bicycle shop income. Yeah, you're really smart. So he has roses and skulls with snakes in them. And a bicycle. Oh, that's so cool. And he is picking. He's, throwing stones. Amazing. That's all you can say. It's fucking amazing. How retarded will they go? The human race. I mean, just how, idiocracy all around us. But I mean, jeez. Shit. It's just amazing. Anyway. Fractal Woman. This was a bit entertaining, actually. I didn't know what to make. I mean, she posted a comment that was just horrible. Very snarky. That I'm baiting her and trying to attack her and all this kind of stuff. And I understand sort of some of these reflexes. I get a lot of grief from people. But, clearly I don't, as the tinfoil hat nutters go. I mean, sorry, we're all in that category, but that's just the way it is. I mean, as they go, she wears it with some dignity, okay? It's just not too ludicrous, as I pointed out in the video. But anyway, so, she took down the comment. I saved it for, when I saw it, I said, she's not going to keep that comment up. It's just, so I saved it just in case I'd need it to attack her later. But apparently, not so bad. Yeah, that was me. Sorry, I was in a bad mood. I can understand that. I'm not really like that. I try hard not to say bad things. Well, I don't try very hard, kind of, obviously. But I really am always defending myself, frankly. I mean, that's all I'm really doing. So, I mean, yes, if somebody throws mud at me, I'll try to pick up more mud to throw back. Really, I'm sorry. Ironically, I actually like your theory. So there you go. I'll take it back. So that very productive. Generous. Decent of you. Thank you. As for your minions, who knows what they're going to do. The minions. Speaking of which, Superior Mind. It's good to have a few. I'm finding familiar patterns emerge between anos and real people. I don't know what that really means. Anons. I guess, is that what you call your mother? Potty mouth. And real people. Let's see. I find it strange that Pyro has studied philosophy, logic, and science. Well, I think that's a pretty poor word. I mean, the bicycle guy should be talking to Pyro, because I don't think Pyro studied very hard, frankly. Berkeley and all. I mean, as soon as you say, oh yeah, I went to Berkeley in the 70s. Yeah. Or, well, 80s maybe. but isn't following any of the logical guidelines for exercising such disciplines. Yes, clearly he doesn't know what logic is. He thinks it's, he doesn't understand that all you can do is add facts. That's all. Logic is just like saying maths, okay? That's all it's saying, right? And maths aren't anything but plus, minus, multiplication, division, and the digits. The digits are the important thing, right? It's without the digits you can't do the math. So logic is just adding and subtracting and multiplying facts. That's all it is. So if you get your facts wrong, your formula is going to suck. And his formulas suck because his facts are shit. So anyway, my added 2 cents. I suppose if one cannot win in a fair fight, they will not use a fair tactic. Well, that's pretty much pointing out that Pierrot's desperation is obvious. And, when you start showing up with the fake evidence and you just keep making statements that have been demonstrated to be false, like, oh, yeah, they've proven it all. They did those detector experiments. They did everything and they know everything. And that's why we believe what we believe. This the God botherer saying, oh, yeah, they found Jesus' sandals and they were really, really worn down, just proving that he did all of this disciple-y looking thingy and stuff, and there was still some water on them and some wine and breadcrumbs and all that, so yeah, proven. Yeah. Anyway, so the lines are manufactured. What manufactures the line? So this, I think I was clear in the video, okay? It's a magnetic pattern. The iron filings inside the glass are lining up just like iron filings would in free space. That is, they're unencumbered by a piece of paper, generally speaking. So they will generally do what iron filings do when you don't have a piece of paper over the magnet. They tend to just clump. And they create a few lines, but I mean, they clump mostly at the two ends of the magnet. And that's what's happening under the ferrocell. So if you put it north and south side up in the ferrocell, you just get a radial lines, just like iron filings. And if you put it north-south going across the glass, you get a clump at one end and a clump at another end, and you see that sort of in the pattern on the ferrocell, and you get but they're all radial lines. So I could make the argument that I hadn't noticed it before, but rainbows have a certain superficial appearance of the same kind of an effect. We know it's an optical illusion. There's no rainbow in one spot. You can go to different spots. There'll be different rainbows all over the place kind of thing. I mean, it's happening in all directions and blah, 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 blah. And it just has to do with the angle of the light. It has a specific angle. You'll be able to see a rainbow. No specific angle, you can't see it. And it's sort of obeying the same rules. I mean, the light's hitting all the water droplets, but how come there's just the one rainbow? And it's kind of the same rules. Okay, the light can only get you from one specific geometric angle. So it's just geometry, as I pointed out. And I'm just saying that, so you're seeing something that really isn't a reflection of what the water droplets are really doing. The argument would be there's no rainbow in the water droplets. The rainbow is just a consequence of one specific angle. You can't throw out the glaringly important feature as irrelevant. I'm saying to you, what you're thinking is some glaringly important feature. That is, you think the rainbow is the glaringly important feature. I'm saying you're concentrating on this little piece of the optics, but you have to understand that that's not what the clouds or the rain in the atmosphere, the water droplets in the atmosphere are not rainbowing. I disagree, however. So the same kind of moron. I like that you were pointing out what you don't like in other theories and arguing why you think they're wrong. Except I don't want you to do it anymore. Radical theories need good scrutiny. No, the whole point is if somebody could scrutinize conventional physics, the radicals would lose a lot of their enthusiasm. It's just that the conventional theory is so bad and so badly evidenced. That's the one that needs scrutiny. Of course, the alternative theories, people who want to modify Christianity or something. No, no, Christians really do love homosexuality, and they're not really. We'll just make a version of Christianity where Jesus was gay, and that kind of nonsense. I mean, it's just. That's what most of the tinfoil hatters are. They really are just conventionalists, and they just want to prove one particular thing. Like it's an electric universe, or it's a blah, blah. And so they're just taking the old religion and they're just giving the Holy Ghost a different role to play. That kind of nonsense. However, you say the light returning has no connection to the magnet. However, you say the light returning has no connection to the magnet. I never said any such thing. I mean, you really can't listen, right? Because you don't want to, right? You just want to believe in your religion. And you just don't want to pay any attention to, it's not even a detail. It's just overt in the video. Of course, I never said any such thing. I'm saying the magnet isn't bending light. It's moving ferrous material. And the ferrous material is moving exactly like it would move without the ferrocell. Okay, it's not doing anything we don't already conventionally, through repeated experiments, already know. It's not doing anything un-Faradaish. That's what I'm pointing out. So this device isn't showing you something it's actually doing. It's showing you something that's just a defect in your perspective. Your perspective is changed by the ferrocell, and now your perspective is like looking at the paper flat on of the iron filings and then being able to shine light on certain hills that are a little bit higher or something, and you'll get a different view of what the iron filings look like. But that different view isn't one likely to give you an understanding of how magnets work. If I actually did this, I put a magnet on a flat surface and then sprinkled iron filings, and then you looked at it at different angles that were all a skewed angle, would I be giving you a good insight into what the iron filings are actually doing? No, it would be exactly the opposite of a good view. It's like a bicycle wheel. You could put it on its side, and do you really get that it's a wheel? Or it could look quite strange. You're not really seeing what it is. That's my argument. However, you say the light returning has no connection to the magnet and the magnetic field. Bullshit. You sort of dismiss it as being arbitrary. No such thing. I didn't say it was arbitrary at all. I said the geometry is exact. And the light's going to reflect off different spiral arms of the iron filings. So what you're seeing isn't something, it isn't a curved line. It's a bunch of little straight lines, okay, like an orbit. I compared it to the orbit of the Earth. And you could understand that the orbit of the Earth is probably a bunch of little straight lines. And of no significance. I'm saying it's of no value in understanding the real concept, just as looking at a wheel on its side doesn't give you much understanding of wheelness. Looking at anything, you can pervert something by just having a bad perspective, a bad viewing angle. I mean, an elephant from above, more importantly, an elephant from below. Good luck with that one. Also, shouldn't you be rebuilding the DeLorean? So again, something else I could write on any dissident channel. Wow, great counter argument. And I'll block you for that one, thanks. I mean, it's just such a waste of fucking people's time. Especially from, look, little guy hiding in the dark. So you have a little dark icon. Where are you hiding from? You think the CIA is after you or something? Huh? Bunch of whatever this is. Solid A. The Eero. What? Fuck you. What, are you smoking your pipe? Pathetic. Anime bullshit. So, yes, I'll give you what you deserve. timeouts. Yeah, forever. I mean, it's even not even a good joke, right? Because I clearly am obnoxious to any kind of time traveling theories. The last thing I'd be doing is I'd be building. If I were building a DeLorean, it wouldn't be for the purpose of, wiping out the future or the past. I'd be working on the present with it. Anyway, so people are just thoroughly despisable pieces of rubbish, and we will move on. All right, so I have pointed this video out before. Double slit thin film, look it up. Surprisingly low number of views for what is a really good physics lecture in a lot of ways. But it's sort of getting to the fact that this interference stuff, this pattern making, making this on-off pattern, you could do it a lot more ways than double slits, and it's just kind of important to understand that, and the important connection is that it always has to do with these surfaces, creating barriers between one surface and another surface. Does a lot of messing up of light, you could argue. It's where everything starts to go wrong. Everything gets a little wacky. And clearly in the slit experiments, my argument would be that, yes, some of the photons are going through transition layers. They're going right next to a surface, which means they're going through the transition layer, which is theoretically the layer that is part of the cause and effect chain that creates this on-off pattern, this light-dark. And these are, just important facts. So, if you, what's happening in this experiment, just two plain pieces of glass. And so the one piece is sitting on top of the bigger piece, and the point is that there's dust that's not cleaned off, and that the piece of glass isn't sitting right on the surface. It's being canted a little bit. So at one end it's a little higher, the end that has the bigger pieces of dust, than it is at the other end, and it's that slope that's causing this pattern, because it's causing constant change in the length that the light travels through the thin layer between the two surfaces, and that's causing it. Now, the thing that people say that this is light dark, it's really, see, if you look at it, you see the dark spots are really the transparent spots. You can see right through them to the shadow. That gets to the shadow line, that gets to the bottom of the table. And so the dark spots are really transparent, and the white spots are more opaque, which is sort of interesting. And then you can see on the edge of the glass that the pattern appears as if it's happening at the bottom layer of the glass, the top layer. And it's not happening at the top layer because you can see the rim of the glass, and you can, that would be obscured if the function was happening on the last layer of the glass. So it's clearly happening on the bottom layer of the glass, is where it's already been created, you could argue, the pattern. So there's little bits that you can figure out here and start getting some idea of things. And so there's lots in the math. They're sort of arguing that whenever you have a transition between a lighter medium and a heavy medium, there's a phase shift. And I would argue that logically that doesn't make any sense. That the phase shift makes sense when you're going through the glass, because that's where we know the light takes a while to get through the glass, and so that's telling you right there that's going to cause a phase shift, right? I mean, if one thing's going this speed, and another thing goes a little bit slower, because even if the path is made longer, but I'm just saying its progress through space is being deterred by something. I mean, obviously that'll create a phase shift. I mean, one thing will be behind the other thing, and that's a phase shift. So that makes sense. But off the surface you're saying that's not a place that generally speaking, you'd say it's anything's getting slowed down. There's no distance the light travels. So I think they have that part wrong, but it's just a matter of following all the phase shifts, because when you have more than one surface you're going through, you got to figure out what surface is the cause, and I think it just gets complicated. And so you can have a general rule that says that's what's causing the phase shift, that you're going from a light medium to a heavy medium, there's a phase shift. But the real truth could be is that rule, is really just a reflection of the fact that whenever you have a surface, you have two surfaces. And so you're really just accounting for the phase shift being caused by going through the heavy medium, not actually reflecting off the heavy medium. So it didn't really get phase shift. It's the other beam that it's going to blend with that got phase shift. So you're confusing the thing that got phase shift with the thing that never got phase shift, because you're thinking the normal, the original photon, was the one that got phase shift, did. And so you're thinking, like I said, you're just, so anyway, I think they're wrong. And so I can go through some of that maybe. But anyway, so there's details to be learned. All right. The truth is sitting here for us to just dissect right here in an experiment like this. And it's just the dissection process, figuring out why this happens. And so the interesting feature is if I make this slope, that is, I push down on the lower part, I'll make more lines. So if I make the slope, the tilt in that piece of glass, more tilt, more lines. Less tilt, less lines. So these are little details, and you got to put all the details together to really dissect what's happening, and then combine them with the details from these other experiments where you get a similar pattern. Obviously, similar. So a diffraction gradient, or some other thing we'll do. It's the same on-off pattern. It's just this is doing the linear thing because the slope is in one direction. But technically, when you're going through a slit or something, the slope is going to be variable, because where the light goes through is going to vary. So you end up with a circle. And then in other experiments, let's see what else. Like the half-silvered mirror, all the little slits that the light's going through, the surfaces, it's going to go through surfaces. Well, those surfaces are tilted in all kinds of directions. So these lines end up being cast in all kinds of directions. And therefore, the pattern isn't lines, it's a circle. So anyway, that's enough. So I guess I'll attempt to draw some of this. Yeah, well, this wasn't a very good drawing. Yeah, it's pretty poor. So we'll try to start over. Might as well start over. All right. And I guess we'll start by understanding the size thing again. Okay, so I guess I will go with drawing. All right. So a photon is something in the hundreds of nanometers kind of size thing. So it's kind of big. So the atom is like 0.3 nanometers. And so, if I could illustrate that, that's the size of the atom, and the polarization, the height of the wave that is your understanding of a photon. I would say the spread of the bits is really big, okay, compared to the atom. So clearly one atom can't be receiving a photon. So if there's a bunch of parts to this, if this was one of your waves, okay, if this was, make this into a little wave going through space, a little wavy thing, it's obviously much too big to be interacting with a single atom. For a single atom to be receiving the information and reacting. It just doesn't make any sense. So it's got to be something that more than one atom does. So the thing to a fact to kind of understand about reality is that metals that are usually doing this, or well, substances, we'll just say, that have this capacity to be transparent or to turn light into electricity, generally speaking, are in the form of crystalline chemistry. Okay, which means the atoms are in tight geometries. They're not just floating around. They're not just they're not just randomly placed next to each other. They're in a tight geometry of a crystal, and so that crystal, the idea of a crystal would just be that the atoms are very well connected to each other, and so their pressure has been thoroughly and completely equalized. So their arrangement of, say, electrons to protons is in some sort of geometry where they're all very happy with their position in the world, so to speak, and can communicate events to each other very easily. So you gotta, maybe I just draw it this way. So I would argue that when they're sharing an electron, they're actually sharing the electron. So this is just a simple representation of the atoms, but that would be the idea. The protons would be equidistant, the electrons would be equidistant, are equally pressurized, which means that if they are closer to each other, they have less force between them, and if they're further away from each other, it means there's more force bits between them. But at any rate, their pressure between each other is consistent. So you could make this geometry a little canted in one way or another. And I would argue that's what polarizes the atom, is you change the shape of the atom, you warp its shape. So if I was to draw that, I would just say, you do something like this to the atom, you stretch, or, I needed one more of those anyway. So you compress or stretch or in some way, change this dimensionality so that the view from this way, from sitting out here, this would say, hey, this is more proton than electron. I could draw the proton a little bigger and just give you that idea that the proton part of the atom is more visible here than it is here, because this electron blocks it. Now, it could be the inverse in terms of distances and what makes it polar. But the point is, it has now a polarity. That is, it looks like a red thing from over here, and it looks like a blue thing from over here, that kind of thing. In terms of what's getting thrown back to you, what reflects back at you, what you see. Anyway, so atoms would be tied together, and so another phenomenon we know exists, and right there in front of our faces kind of thing, is let me get rid of this kind of ugly thing here. Sorry. Yeah, that's the only problem with this drawing stuff. You gotta waste some time switching and such. So, is reflections and that sort of thing. So, something comes in, okay, and it does this equal place out kind of thing. So you could draw a line. Just keep the blue and red theme, I guess, right? This would be your normal, okay, and the angle in is the same as the angle out from the normal of the surface, and then the bending, okay, into the surface is well, I got the wrong color. We'll do bending in green. So it came in this way. We can just put the arrow on there. It's okay. I don't think anybody will put me in jail for that. The bending is this way. Right? Okay, to whatever the other surface is, and this angle is a compound reflection of the other angle. It's skewed in this direction. believe. And then when it goes back out again, it returns to the same angle, but it's now leaving at a different position. So it's now, if you were to take the original beam, it would have been here, and this beam comes out here. But they're both now still parallel. And all it did was, while it was in the medium, it had a different direction. And it goes back to having the right direction when it comes out. It's not a very good illustration of it, but it'll have to do. And so the point is, with this whole these issues, is there's all kinds of reflected elements that happened when this photon, there's a percentage of the light that will reflect, there's a percentage of the light that will transmit, then when it hits the bottom surface, there's a percentage that goes out, there's a percentage that reflects. So you can think of that as what happens to an individual photon as an odds thing. What's the probability of reflection? What's the probability of reflection here? And then you get this whole internal reflection argument. That's all part of what's happening, and the phase shifting that's happening to the photon. So I was of the opinion that photons did interact with individual atoms. Now, that's wrong, clearly. So they are being collected by a crystal in the substances, which, whatever. So it's a collection. So what a bunch of atoms are sensing the world. And those atoms are connected, and by being connected, they're experiencing each other's pain, so to speak. All right, so if I was to bring a photon, that's, these are already smaller circles, so that'll work. Okay, so here's a photon heading for this electron. The argument sort of is the photon is, now, the distance between them, that is this frequency, is going to be always the same, this period, okay, of, to be detected as a proper photon. And the idea is that when this photon hits the electron, it's going to cause a certain reaction in the electron, and that reaction is going to cause this reflection or this other stuff that's going to happen. So the curious fact is, all right, is that you can sort of see from the picture that maybe none of these pieces will hit this electron, and only this one little piece will. And so what's going to happen to the one little piece when it goes into this pressure? Okay, so we have the pressure of these electrons. So you have to understand these electrons hate each other. So there's a tight pressure between them, and they're attracted to the nucleus. So they're being pulled in and they're being pulled apart. And that's the tension they're in. So when I hit it with this little bit, this electron, you could think, okay, it's going to get momentum in this general direction, okay, but that general direction is not acceptable for it to move in. So if it moves this way, this electron says, no, that's causing me pressure, and that's my pressure is backed up by this guy's pressure, and this guy's pressure, and this guy's pressure. And so in a sense, the electron's not going to move this way. Its momentum is going to carry it this way, and it's going to end up being pushed back into the location it was in, but it's just going to do it in this kind of circular path. And in each one of these processes, to change its direction again, it's going to require there to be an event, and the event will be it's going to get hit by a little piece of energy. Just like the photon in here, a little piece of energy is going to change its momentum, and so it's going to move back to its position. And the process of being moved, just as it had to absorb something to go in this direction, it has to absorb something to go in this direction. And what's going to happen is that exchange in momentum involves re-admitting the little photon bit. So that's the angle in, angle out. So that's what's happening when something's getting reflected, is that it moves the electron takes the path, and when the electron stops here, that's when this pops out. So essentially it's an absorption of energy in this direction from the universe that stays in the electron, and it gives back this little bit, and that's the reflection. So that's one way the electron can behave. Is it's pushed, it's moves. I've exaggerated how much it's moving here. Obviously, it wouldn't move that close to the proton, or it would end up just going right into it. Blah blah blah. It can't get out of the tension here. It just really just wobbles a little bit in that circular way. It processes a little. It's a little hook in its direction. But the point is that the converse energy is this opposite angle. That accounts for the equal but opposite reaction kind of thing, you could say, in a way. So this little piece would go on its way. Now that's just one piece of a photon, so it's kind of useless, right? It doesn't have a frequency. It doesn't with a gang, because it only was one single electron that hit there. And that looks like that's going to be just a lost piece of crap, right? I mean, I drew this with, just a time thing, so you should probably ignore those dots, because there's only one dot. And one dot does not a photon make. So the point would be is that these other bits will likely hit other electrons, okay, because they're much further apart than the size of the atoms. So they'll also experience the process of hitting electrons, and they'll do the same little thing here. So then it might get back some more of its substance, so there might be 6 or 7 of these things regained, or whatever. If there was 10 to start with, there might be 8 coming back out. There might be 7. But the point is that some of these bits won't do that. They won't hit a surface electron. They'll go deeper into the material and hit one deeper. But eventually, some percentage of them will be thrown back out at this equal angle. But what's really going to need to happen is that another photon, that is another clump of this stuff moving at a frequency, is going to have to hit and do the same thing. And what's going to happen is the two photons will essentially be, half of each will be combined to make the new photon. And that might have to do with what colors you reflect out of a surface as these combinations. So taking it to the next step, so you could sort of understand that if I hit the surface with something at a sharp angle, that this loop would end up being in this direction, and it would just sort of obey these rules. And that if I am at a sharp angle, I'm more likely to interact with electrons. So the sharper the angle, the more likely it is I'm going to hit electrons, because the electrons are on the outside of the atoms. And so if you have little humps and then you bend that towards something, you can understand there's more surface area to the humps, right? So if I had a bunch of bumps on a surface, a bunch of bumpy surface, okay, when I'm looking at it straight down, I can go in between the bumps. But when I look at it from this kind of angle, I can't do anything but hit bumps. I mean, all I do is hit the mountains. You know what I mean? So if I put mountains on a surface, I always hit the same sides of the mountains. So it's more likely to reflect. So that makes sense. These are all the little details you got to keep track of. So the point would be with frequency dependence is that if this electron gets hit with these little bits faster than it can do its loop around here, that is, the frequency of the bits are coming at a fast enough speed, the electron won't just do this little swingy thing. The electron will start to move in this kind of direction, because it won't have time to do its rebound. The pressure won't have time to tell this bit you can't go here. Okay, so it's going to get pushed into a position that's much further out of alignment, and then this reaction is going to get stronger, and that means there's going to be more reason for this electron to actually do the moving. So instead of this one doing the rebound, this one's going to essentially be a participant in the event. And it's sort of like sound propagating, in the sense that you're exchanging electron motion now. Instead of the electron doing its loopy thing, it's moving so fast, such a very short distance though, but it's very quick, and so the other electron thinks it's closer to that electron, and it just moves away the same amount. And so the energy exchanges between the electrons of the atoms, and that's when you have an electric current. So if you can hit the electron with little bits at a fast enough rate, they don't rebound, and they just keep being pushed further into the tension. And when they're pushed far enough into the tension, they'll cause the other electrons to essentially do the same thing at the same rate. And so you'll have a cascade of the motion of the electron. And that cascade in motion is electricity. And the byproduct of that cascade in motion is that you changed the relationship of the electrons, which means you changed their appearance here. You've polarized the atom. So while the atoms are transmitting the electricity, they're getting thin, fat, thin, fat, thin, fat, thin, fat, thin, fat. They're changing their polarity as they move the impulse from one atom to the next. So the atom that's thin is essentially spreading the pressure that came in and making the next guy thin while he gets fat again. And then this next guy will get thin and he'll get fat, and he'll get thin and he'll get fat. So it's moving the electricity at the frequency of the light, essentially. Substantially. All right, so that's that's not dealing with facts. That's dealing with me explaining how a set of facts, if you can understand that this is the kind of motion there is, this is what it could lead to. So this explanation explains the conversion of a photon into electricity, and why it's dependent on frequency is because if you don't hit it fast enough, the electron just does its little loop around and just readmits the energy out to space. So the complex part is now when you're talking about what part of the photon gets through the surface. So let's just clear it and do some of that, I suppose. Just getting complicated. We need the pen again. Yes, I hit the pen. I just want the pen. Don't want the options. Anyway, all right. So the Science Asylum guy did that video on how mirrors reflect, and the idea is that when the photon's coming in, it's not just bouncing off the surface. The photon goes into the surface and hits atoms too. And it can be 15, 20 atoms on a good mirrored surface. The metals. Deep is where you're still getting reflected light. Okay. And again, it's frequency that's going to decide whether you turn this photon into something that just reflects, or whether you turn it into something that causes the flow of electricity, that is the pressure of the atoms to push against each other and create a current eventually through the crystals. The crystals create the little jolt across them, and then at the seams of the crystals you could sort of understand that the electricity flows through the surface. And the same would be true of glass, because the ironic part is that you have all this crap happening. You have these different depths that some of this stuff is reflecting, and then you got, the fact that at the other end, somehow it comes out of this end of the glass still a coherent number of photons representing a certain amount of energy that came in this side. And that's what the crystals are doing. The crystals are kind of guaranteeing that none of this energy can go too wacky. I guess the other point I wanted to make was, yes, to understand this, well, I sort of did the angle in, angle out. Oh yeah, the point I wanted to make is, so if you're hitting an electron here, let's say, and you were going to hit it with energy, that is a frequency, ultraviolet or violetish light, tight frequency. So you're going to hit fast. Okay, hit, not hit. You're going to hit it fast. That this electron essentially will move in kind of a not perfectly straight direction. So the light comes in this perfectly this way. So you would say, well, then the electron moves this way. But that's the other point, right? Is that these atoms were all connected, and it's connected to other electrons. So it doesn't move the direction of the photon. It has to again fit with the balance of the other atoms. And so instead, it has a bias in, say, this direction. So that's what's causing the diffraction in the material, is that when you do convert it into, when you're hitting it enough, or you're hitting the electron and moving its position, that it moves in a certain path. And so in a way, you could argue that glass is electrical. As much as it doesn't transmit current, it's not a conductor, it will transmit a kind of electric pressure, and it just does it at an angle that's going to be bent a little bit by the fact that the electron isn't in free space. It's connected to other electron pressures in all these places, and so it will bend based on the pressure it's feeling when it moves. So even though the energy came in this direction, it'll move in, I know I should make it more dramatic, it'll move in that direction instead of going this way, because it's this pressure between these other electrons is forcing it to move in a different direction. And that's going to change the direction of all the other electrons that are pushed in that piece of the crystal, and then eventually this whole thing somehow, again, ends up being coherent when it comes out the other end. But anyway, that's, like I said, it gets kind of complicated. So the real point, takeaway points, is that you can understand the angles, and the angles have to do with the pressure the electron's in. But the other thing to understand is that a single photon is not interacting with a single atom. It's spread over various atoms. So the photon comes in a bunch of these little bits at a frequency in terms of their arrangement. And some of the bits reflect. So the photons are essentially broken substantially by the surface. And what's really going to happen is they're going to recombine, okay, when after this process of what bit, this bit got reflected, this bit got went through deeper, and this bit was combined with another bit that moved an electron. So it's getting all broken, but the fact is that when you add up all these reflections from all the different photons coming in and the ones breaking into bits, that a certain percentage of each photon is actually what's reflecting. So if 5% of the light reflects, it means something like, see, it's really hard to measure all this stuff, energy. You don't have any great experiments that quantify exactly how much energy went in and exactly how much energy goes out when it comes to light experiments. It's hard to do. It's hard to even make X-ray detectors and that kind of stuff. Hard to make them. Ultraviolet cameras are a lot harder to make than infrared. Anyway, I have to look into some of that stuff too, just to see what evidence there is of the problem of combining. So you'd have two infrared photons that are out of phase, could look like an ultraviolet photon, right? But we don't see that happen when you put two laser beams on a spot. It doesn't look like there's any combination. But maybe it just doesn't look like because we don't see it. We can't see if there's more ultraviolet light being created. You have to have special tools to do that. But anyway, that's the only part that gets complicated, is figuring out what possible consequences is there to this fact that essentially photons are broken to pieces. 5% goes this way, 20% goes this way and reflects again, bounces off the bottom and reflects again or something. Another percentage does this, and really it's about all these rays coming back out and what they're combining with. So technically you can have an internal reflection that ends up combining with a new photon coming to the surface and creating a new photon out of that. So there's lots of complications, and I guess that's why we haven't seen too many single photon experiments done with interferometers or with these more complex optics. And that sort of needs to be done to see exactly what's mixing with what. So this is the part where I still haven't got a hard picture to show you, only a theoretical one where you can sort of understand that if there's an internal reflection that is smaller, okay, than the crystal, all right, so this isn't thick enough for there to be a whole bunch of, a very long distance between the reflections. So the reflections have to be little reflections. You could sort of understand that they'd still be affecting the same crystal, the same row of atoms, and that you could essentially, the reflection that came out in, say, the reflection here, and the reflection here, the transmission. So this one went up. Some of it reflects back, but some of it goes right through the glass. So you could sort of understand that the one that's bouncing here could come out at the same time as another photon that's a phase behind comes out. So it's been phase shifted exactly the same amount, and so now they're both coming out, and they're coming out where you have the necessary period between them. So they've been phase shifted, and they're essentially rebuilding a photon based on their phase shift. That the fact that this took time to go down here and go up here took time. So while this was just doing this one was doing this, and they're recombining to create another energy that's coming out at still the same within the crystal size. So within this limitation of 1,000 nanometers in distance, and let's understand the atoms are 0.3 nanometers, so that's a lot of atoms in that distance. This is essentially what we would call a single photon would cover that much area. So a single photon could be emitted by as many as 1,500 or 2,000 atoms. So the distance of a couple of thousand atoms is really a pixel of light, in the sense that one photon can be emitted by that entire surface and still be of the right polarization in terms of its wave height, if you want to make that argument. Its wave irregularity, whatever, its displacement of space. Yeah, so that's probably enough. So, I have to do more thinking, but I'm just saying just those basic facts about how small atoms are, how technically big photons are, in terms of how much space they can cover in terms of their wave displacement, kind of indicates that photons aren't reacting with single atoms. And when they are in space scattering, that the scattering is a byproduct of pieces of the photon getting broken off and then recombining with other broken photons to create the photons we see. But yeah, photons break, I guess is the takeaway, something like that, and are remade. So I have to think of a good way to say that. It's like throwing ice in a cold plate. You throw the piece of ice, it breaks, it shatters, and then it somehow recombines. New pieces melt to each other, but you end up with the same stuff essentially going out. It's not a great way to explain it, but essentially it's something like that. It's in a form. The form is deconstructed by the material, and the material ends up reconstructing something that looks close enough to the original that we're fooled. Alright, so that's probably enough. So, till the next time, and such, and so forth and whatnot. Yeah, I think that's enough. It feels like enough. Might only be 40 minutes or something, but it feels like enough. I'm tired. Shouldn't that be good enough? I probably should just pause and see if I think of something. So maybe I'll do that. I'll just pause. But it's probably the end of the video.